Hello and welcome to a slightly unusual Tachyon Tuesday. My name is Jason Keogh and I'm the Partner Chief Technologist for 1E, and today I'm going to be using things in my kitchen to explain why Tachyon is better than its competitors. Essentially, what we're going to be talking about is the how. Last time on Tachyon Tuesday, the blog I wrote was about non-functional requirements and that the how is more important than the what. So essentially, that's what the topic of this session is. And I was describing it to my son, who's 13 years old, last Tuesday, and I used an example with jelly beans, and I don't have enough jelly beans to do this, but I do have enough grains of rice. So bear with me a second, we'll have a look at what we're doing here. So this is the setup, okay? And what we're going to do is the rice in this bag is going to be data. And essentially each of these shot glasses are representing devices, maybe even many devices, thousands of devices, but each one is going to contain a set of data. And this in the middle is a central database, okay? So we're going to be taking data from the devices around the edge and putting it into the machine in the middle. So this is our starting point, right? We have data in the devices and we don't have data in the database. And what's going to happen is that over time, each device puts a bit of data into the central database, and each device might be putting in, they may be putting in 50 or 60 or 80 different metrics worth of data a minute. So over time, this central database builds up more and more and more data. Now, on a lot of tools out there, what they do is they just send back all the data all the time. So they'll stream data into a central database. Sometimes they might drop some packets, but they stream data into a central database, and over time that fills up. So over time, our central repository fills up with data, and in the real world, the devices don't lose data, right? They build more data over time to keep on sending the data in. But I have a finite amount of rice, so go with me on the analogy here. So the thing is that sometimes what's being sent in, is not just another piece of data that everything is fine. Sometimes what's being sent in is something a little different. Enter Rocket the raccoon. Okay, so this little toy from my aforementioned 13-year-old son is going to be our interesting point of data. Now the thing is that when it comes in, it literally drops in and it is assessed. These devices are all sending in thousands, tens of thousands of pieces of data a minute, right, between them, because you've got tens of thousands of devices. If each one is sending 50, 80 different metrics a minute, you have hundreds of thousands, perhaps millions of pieces of data per minute to assess. And when another piece of data goes in that is interesting, it's going in with all of the rest, and essentially something has to search through all of the grains of data to identify when something in there doesn't seem quite right, doesn't match the same criteria as the rest, and it's something that we need to be aware of. Once it's established that Rocky Raccoon is in the rice, it then might tell a device to do something, right? So it sends an instruction and says, go over there and do something inside of that little beer-shaped shot glass. So that's the the process that most of our competitors go through. They send data in continually to a central point. They assess that data when it gets to that central point. Based on that data, being different, they will trigger a reaction. So there's an amount of time that it takes to send the data. There's an amount of time that it takes to assess the data. There's the amount of time that it takes to send the reaction, and then the reaction actually starts. Plus, what you have in that center is a lot of data. So when you want to understand which devices match certain criteria over time, well, you're going to have to look through a lot of grains of rice, right? Maybe terabytes or even petabytes worth of data to find which device has made a connection to a given IP address in a given period of time, for example. And that takes a long time to examine. So this is the Tachyon model. We do still have a central database with some rice in it, and we still have data in all of the devices. However, we leave the historic data about what's going on the device. Typically, once or twice a day, we'll send in the it's all fine data to the central database, so the averages of CPU or whatever. It's only when things are out of whack, when something happens that we don't want, that we actually send something immediately. Okay? So there's much less data being transferred in the first place, which makes it more suitable from a scaling perspective. Secondly, when we want to monitor for whatever trigger, we want to monitor for data out of bounds or something crashing or some issue in a log file, we send those things we want to know about to the endpoints. We send the data from here out to here. We don't store the logic in here. The logic is sent out and distributed amongst all of the machines, which means that, when we have a Rocky the Raccoon moment on this machine over here, that machine assesses, when that thing happens, the trigger here, and this is guaranteed state inside of Tachyon is the function, the trigger here is, something crashed. And Tachyon knows how to react to that particular crash to resolve the issue. So it reacts to that particular crash and it resolves the issue entirely independently. In other words, if the network connection, between Tachyon and that device were entirely broken and that device were isolated on its own over here in this logical part of the countertop, that would be fine as well, because the machine knows how to react to a Rocky the Raccoon moment. Actually, that's Rocket rather than Rocky the Raccoon. Very important. Get your Marvel characters right, especially when you've got 13-year-old sons. So basically, and who doesn't love Marvel? So basically what happens is when this thing occurs here, it reacts instantaneously in real time. No sending a message, no assessing the message, no sending a response. It just happens and it's reacted to. And what happens then is we actually send the message in to say, hey, this happened. Okay, so we reacted to it, and this is the result of that reaction. So we do know at the center, essentially in real time, it's going to be within a second or so of the thing happening here, as quickly as though we had been in the previous scenario. But the difference is the problem is already fixed when we get alerted to it. The action that we said to take when this event occurs has been taken. And it's just a much, much faster way. And also the actions are much clearer and easier to find because they're not surrounded by so much gumph. Now, the other thing is that if all of that, rice that's in all of those different containers around there were in the center, and I wanted to find one particular grain of rice, it would take me a long time to find that grain of rice. Okay. So essentially, instead what I can do is when the data is kept out at the endpoints, when I want to find out which machine has made a connection to a given IP address, as per my previous example, rather than searching through all of the rice in the middle with all of that rice in the central database, which is maybe several terabytes of petabytes of data, each individual machine probably only has 50, 60 megabytes of data in it. Okay, and you can search a 50 or 60 meg database really, really quickly, and I mean in milliseconds. So essentially we can send an instruction to the devices simultaneously to say which one of you have made a connection to this IP address, and each one that matches that criteria will send a response back to us. And that's so much faster than searching in a large central database. And that's one of the reasons Tachyon is so fast when we actually see it running. So this concept of a distributed data system, as evidenced by mismatching shot glasses and rice in my house, is one of the key things as to why Tachyon is better, because it's an architectural difference. It's the how it's done that is different. And essentially it's very difficult for other systems to scale or react in the same way, because they would have to re-architect how they're built in order to do that. Plus, Tachyon was designed from the ground up to be something that monitors for and reacts to stimuli, triggers as we call them, inside the guaranteed state rules, and then reacts to those. And it was designed with our largest customers in mind. So we already had customers of 500,000 endpoints when we started building Tachyon that were running Nomad and so on. So putting this together was was obvious to us when we started building the technology 6 years ago, and now we can see the dividends as we work with accounts both large and small. So speed is very, very important under certain circumstances, particularly when there's a user here presses a button and expects something to happen. That needs to happen immediately. We don't want to send a message back to base, assess what needs to happen and send a message back to the end user. It needs to happen immediately. When somebody central, like a sysadmin, is trying to help a user here and wants to gather some data, from this machine, they want to get that data fast. They want to look at the data in that machine, about that machine, on that machine, and ideally without needing to interrupt the end user, right? You don't want to have to tell the end user, please, I'm going to screen share, please step away from your keyboard and mouse, I'm going to take control. You just want to get the data and get the job done and fix the problem for the end user. And that's, those are the promises that Tachyon makes, and that's basically what we facilitate. We can't remove all screen sharing, but we can massively reduce the amount of screen sharing and interruptive time taken from the end user that you would see compared to other systems and people using other things for support. So here endeth the slightly strange Tachyon Tuesday, the first one without screen grabs. Who knew? I hope you found it interesting. Thanks.